Thanks for coming. So today we have a home group from Warwick and talk about Clique and Theorem.
Right, yeah, thanks for having me. It's glad to be back. So where I should look at the camera? Oh, it's there. Okay. So, right, today I want to talk about a type of problem that so-called Erdős-Rademacher type problem. So, it's very classical problem. You fall into this shape of questions. Basically, we ask for what kind of conditions will guarantee some substructure. Right? This is the things we're looking at. So, in particular, in this case, the conditions we cared about is usually the size of the graph, how many edges, the number of edges in your graph. Okay, usually we assume n is the number of vertices. Consider n is a fixed large number. Then you say, okay, now I give you this many edges as a graph, and what substructure you can tell me that must exist in the graph. Okay, in the particular case, what we're going to talk about today is mostly going to be we want to find cliques, the most common graph that we're looking at as a first case. Okay, the cliques. So, rather a little bit vague so far. So the birth of extremal graph theory can be considered to be started by the following result. Of Mantel and later generalized. This is in 1906 or 1907, 1907, and later generalized by Theorem in the 40s. Basically, if I phrase it this way, is that if you have an n vertex graph, and if your number of edges is bigger than, let me just write it as so-called the Theorem number of edges, I will explain in a second and remind everyone, then you will start to strictly bigger. Then we will start to see the substructure that we would like to see. Okay, so this is in the most simple form. Let's take r equal to 2. Then this t sub r of n is the number of edges you will see in the complete balanced bipartite graph. So you have a complete partite graph where the number of parts is 2. You have all the edges in between. The size is n of 2. The ceiling. Okay. And in this case, if you have more than this many edges, which is roughly n squared over 4, Mantel's theorem tells you that you will for sure see a triangle. So this is the simplest demonstration of this type of result. Then let me dive right into the problem I want to talk about today. This clique minimization is what happened after this point, right? When you go beyond this bound. If I rephrase Mantel's result, basically it's saying that if your number of edges is 1 above, then for sure you will see one triangle, right? Then you will see one triangle somewhere in your graph. At any point if you have questions, please let me know. And right, so this is precisely what we're talking about. We have the condition, number of edges, force this substructure. But Rademacher, this is the beginning of this problem I want to talk about. In 1941, 1 year after Theorem generalized it to all cliques, he observed in an unpublished note, he observed that when you have one above this threshold, then not just one triangle they will see. You actually see linearly many triangles. So what he proved is that if you have at least this many edges, then you will actually see n over 2, at least n over 2 many triangles. Okay, so you will see linear in n, in particular n over 2, and this can be easily seen as optimal bound here because of this complete bipartite Theorem example I drew here. Because in this graph, if I add an edge here, then all the triangle must involve this red new edge, and there are, oh, I should add it on the other side, or I can just change this. So, right. So all the triangles must involve this red edge. So you will see that the number of triangles is precisely this. So you cannot go, we cannot hope to get more than this quantity. Okay. So this is really precise results. It's very nice, but we are just scratching the surface because the total number of edges in the graph is n choose 2, and we are just barely at edge density 1/2. This t sub 2 of n is this equals to n squared over 4 plus 1, if we forget about the floors and ceilings. Okay? We are still very far away from the total number of edges. So what next? Let's give a brief history that leading up to the big conjecture. So next is, of course, Erdős come into play. In 1955, after 14 years of the observation of Rademacher. So there's an exercise here. So let me recycle this E. So Erdős in 1955, he asked the following question. Okay. Basically, this is the question I want to talk about today, and the name nowadays is well known as the Erdős-Rademacher problem. So what is the question he's asking? He said, then basically generalize this observation. He asked how many cliques we can see, we guarantee to see. Okay. Let me just write it like this. This usually just a shorthand to write among all graphs with m vertices and m edges. Okay, this is just. So if you look at, we always fix n as number of vertices. So you look at all the graphs with exactly m edges, then which one minimize the number of triangles, say, or K4 and K5, right? We want to look at the minimizer. Or in other words, how many you can always guarantee to see. So if we define, so this is the key function that we're interested in, so definition, then we can define G sub R of Nm to be the minimal number of KRs among all m vertex m edge graphs. Okay, so this is what we want to study. Basically, now if I write it in terms of this function, Erdős' question from 1955 is asking us about to estimate what is this function, how does it behave, G sub R of Nm. So let's do this in this language. Basically, what Rademacher observed, let's write it in this way. Is G sub 3 of n squared over 4 plus 1. Okay, we have among all m vertex graph with n squared over 4 plus 1 edges, you can always see n over 2 triangles. Let me just forget about floors and ceilings for a moment. Why equality? Well, upper bound comes from the construction. So upper bound is this construction, right? This one shows that you cannot see more than n over 2. And lower bound, you have to do some work. You have to show that no matter which one you give me with this size, then I can always show you there are this many triangles. Okay, so that's his result. So usually the harder bit is the lower bound, is to prove that no matter which graph with this size, I can always find you this many cliques or fixed size. Okay, so what is the history? I haven't. Let me talk about the prehistory to the problem I want to discuss today. So the prehistory about this problem. So after Erdős posed this question, let's see. History, part 1. Okay, so what happened so far up until then? If we look at just the, let's look at just triangle case. That is to say, we cared about when r equals to 3, okay? R equal to 3. So in this case, obviously, let's make a table. Mantel's theorem tells us everything that we need to know up until t sub 2 of n. Here, it's 0 because we cannot guarantee to see anything, just taking a bipartite graph, okay? This is what it's saying. Then Rademacher, that's the result I just said, give us the exact answer for +1, just 1 above. So now I'm slowly getting into what I mentioned earlier, that we are really far from the whole picture of the minimum number of triangles you can see. So gradually, the next one, Erdős himself, in 55 and 62, these two papers, the first one is where he raised this general question about, he solved all the cases. Now he goes a little bit more, linear number of edges more, okay? Plus some small constant epsilon times n. Then, Loras and Simonovich in 76, they go all the way, again, still stops at edge density 1/2, but they managed to push it to n/2. So the significance of n/2 here is that this phenomenon carries over up until you have n/2 more edges. So whenever you have an additional edge, up until you have n/2 above the Theorem number on 2 parts, then every additional edge, you get n/2 more triangles. Okay, so it grows linearly. But then when you have strictly more than n/2, you can make it slightly unbalanced, and you can do better. So this answers the question of Erdős, but still, we are still at the edge density 1/2. So one of the very long paper in 83 by, let me put this up. Okay, so this is up until here. Now, the next result I want to mention is again by Loras and Simonovich. This is the 83 paper, I believe, 83, 86. Let me just double check. 83, right. So what they prove is actually they resolve not just for triangle, and also for all fixed size clique, the clique minimization problem, when the number of edges is around Theorem density. Okay, so what they managed to prove is that they resolve, in particular for triangle case, the number of edges between, okay, so if your graph, the number of edges is very close to, this epsilon depends on k, the Theorem density, meaning that this is when k equals 3, right? If your edges is very close to this particular graph, Theorem graph on 3 parts, then they have a complete picture of how many triangles or fixed size clique you're supposed to see, and even they characterize the structure And this is a very long paper, I mean 30 pages with case, they have step A to U, the capital letter U. So, and it is precisely in this paper they made the following very bold conjecture. So this is the problem I want to, this is basically a precise formulation of what Erdős wanted to ask. And if true, there will be a complete solution to this problem. So this is the, in the same paper, they conjecture, Warwick and Asymptotic. Well, actually, they already conjectured in the previous paper. Here, it's a very special case, conjecture. So what's their conjecture? It can be very succinctly described as there exists the Clique minimization problem. There exists one minimizer that looks like okay. So I have to explain what's going on here. So this is the question I want to talk about today. So what I'm talking about. So what they're saying is that if we given m vertex graph and we know how many edges there are, m edges, then and we fix R, our favorite R, you want to look among all nm graphs, the minimum number of KRs, then among all the minimal, the minimizer, one of them must look like this. You have a complete partite graph. This is a complete partite. Maybe the size could be different. Let me just make it slightly more general. Right? You have a complete partite graph. That's one part. And then it's completely joined to another part. And here, this other part is a triangle-free graph. Okay? That's their conjecture. Now, this looks a little bit strange maybe at the first glance if you have not yet previously worked on this type of problems. So let me motivate you. Let me give some explanation why this question. Is the question clear?
Say TK and the Logasimov is get K same as R or?
So if we always fix our R first, so let's say you want to do K4 problem minimization,
right.
So R equal to 4. Then for any K, at least R, I guess, because when K is smaller than R, it's always 0.
Yeah.
K
so
smaller
that
than
K could be different than R, I think.
Right. Yeah. So for any Theorem density above R, around that tiny window, they can do it. So later I will draw a picture. I will show my drawing skill that I've been practicing. So for this one. So why this peculiar question? At the first glance, I have well, yeah, this is really a bold conjecture because basically it's a very complicated question, and then they use this very short form to basically, if it's true, then you will completely answer the question. So why? First of all, why this question? Maybe let's look at a simple case when R equal to 3. So suppose we want to minimize the number of triangles. Okay, we want to minimize the number of triangles. And suppose we also restrict our attention to just the first non-trivial interval, meaning that let's restrict our attention, the number of edges, to be above the two-part Theorem graph, above n squared over 4 edges, and below, let's say, T3 of n, which is this guy, n squared over 3. Okay. So up until Lovász and Šumowicz made that conjecture, it was already known in this prehistory that they figured out that if m exactly equals to the size of the two-round graph, all these countably many points, if exactly equals to these, then two-round graph is actually the unique minimizer for triangle minimization problem. So for this infinitely many, countably many points, we do know, okay, this is measured 0, right? It's not solving the problem. But what happened in between? What their guess is basically kind of like an evolution, like you growing. Let me show you. So basically, their conjecture is, if you want to know this interval, then basically you start growing a third part. Okay, from here you make this n/2 slightly smaller. You start growing the third part, and make sure this two part is of the same size. Make them complete. Okay, look something like this. Now, if you gradually change m towards n²/3, then eventually this yellow part will grow to be as big as the other two parts, to be of size n/3. So this is like a smooth interpolation, right? The transition between t⁻2 of n to t⁻3 of n. And basically their conjecture is saying that this kind of smooth transition basically gives you predict the value of the minimum number of triangles you was always guaranteed to see. Okay, still we're not quite there yet. Why this triangle 3 kicks in? So imagine, suppose this is true, then because this is all complete across, right? I can grab two parts here and just replace it by any triangle 3 graph. Okay. Now, where we see triangles? Definitely not in this red box, right? So all the triangle has to look like one edge in the red box and a single vertex from outside, because this is complete. So that means as long as I preserve the number of edges inside the red box, I'm not going to change the triangle count. So I can replace this red box, the complete bipartite graph, with any triangle 3 graph that I like, with the same number of edges as these two parts. Okay? So this gives rise, if the original guy is the minimizer, then this is also a minimizer, because I didn't change the number of triangles. And now, if you look at, that's precisely what they conjecture, right? So they say that, okay, maybe we have to do some basic optimization to optimize the part size. But if you forget about the part size for now, the one of the minimizer, it looks exactly like how we get over there. That's the kind of like one of the reasons that they came up with this conjecture, both conjecture, right? So you have the complete part-type part here, completely joined to this triangle 3 part. Okay, any questions so far? Yeah?
Is the number of paths determined by the big size here, or do they just say that it should be complete?
Yeah, they didn't say, but it's not so hard, because now this class of graphs is a lot more restrict. So you can do a basic optimization to determine.
Yeah.
And turns out the number of parts, it really depends on the edge density.
Okay.
Okay? Yeah. Depends on the edge density.
Does it maximize
like exactly like this. So if edge density is between these two parts, then you will have one part outside because you merge two. If the edge density is between 3-part two-run and 4-part two-run, then I'm going to grow an additional part, right, to get the 4 part. Then the number of parts outside is 2, and I merge this tiny new growing part with one of them to make it triangle 3. Okay.
Right.
So this is the formula. Well, how you get there is simple optimization, because this is the complete part-type graph. You can just write it in terms of like reals, right? And the sum, you give weight to this part-type set. The sum of the weights is 1. You compute and optimize, and that's what it spits out.
Are you saying that there's a unique optimizer? No. Right?
No. I'm saying that so yes and no. So what I'm saying is that suppose we are still in m between n²/3 and n²/4, right? Our favorite interval, the first non-trivial interval for triangles. Then yes to your question is because we have precisely one part outside. Okay, this is Cn for some C. And here, let's say it's 1 minus 2c times n, okay? Then I make this complete. Yes, because this is fixed. It's a unique ratio. You can compute the edge density to make sure that the number of edges here is the m here you keep them with. And no to your question, because now, after we get this minimizer, I can change this to triangle 3, maintaining the same size, right? Okay, so this one can all be computed and is uniquely determined by your edge density by, let's say, m over n choose 2, right? Look at your edge density and you can compute that. Okay. So we managed to mention this main conjecture. So what do we know about this one? Right. Okay. So let's see where we should go. So this is the prehistory. We're going to talk about more recent results.
The complete bipartite graph, is it balanced partite graph?
The answer is yes, but they don't have to specify it. Because if I know one of the minimizer is complete partite and a triangle free, then among this family I can do optimization, and it turns out they have to be balanced. So the answer to your question is yes, but they originally didn't phrase it that way because that's implied, yeah, after optimization. Okay. So right. I think maybe I should erase this. I forgot what I want to say. Oh, okay. So turns out this question is difficult. So let me first give you the first reason that why it's difficult. Okay, this question. Okay, the original conjecture is difficult. No kidding. So what do I mean by that? Well, they made this conjecture, right? There's this family. One of the minimizer must look something like that. Then now I can define this family. Let's say I call it H and M. So what is this? Now we originally Erdős' question is that if you look at all the m vertex m edges graph, then he asked which one is the minimizer. And Lovaas and Sumanov is basically saying that you don't need to look at all the graphs. You just need to look at this very specific H family somewhere here. Okay? H and M. And as we just discussed, because this H and M has so specific structure, we can actually carry out computation to find out the exact value here. Okay? The given N and M, we can compute the number of, we can do minimization at least over here. So let me just define H, there's a sub R, but let's focus on triangle again for now. And M, what is this? This is the minimum number of KRs among H and M. Okay? We look at a more restrictive family. So then, what do I know? Well, by definition, our original parameter that Erdős is interested in, the minimum number of KRs among all graphs, of course, this is over a larger family, right? It's over a larger family, so this is going to be smaller than this minimizer over the smaller family. This is what we know. And rephrasing Lovaas and Sumanov's conjecture is saying that equality holds here. Okay? This is their conjecture. Now I get to the first point why this is difficult. Well, because this can be computed, now if we compute this one, I will draw you a graph. But before we do that, let me define one more thing, then I'll do that. It's the asymptotic version, okay? Whenever the problem is difficult, what do? We look at the easier problem. So that's the asymptotic version. So what do I mean by asymptotic version? Instead of looking at this guy, I don't really care about M that precisely. I just cared about its edge density, right? So what I mean is small g, let's say sub r, of lambda Okay, let's take a moment, look at this definition. So this is basically saying that now, instead of looking at M edge graph, I look at graphs with lambda edge density, okay? And then I look at the minimum number of KRs among all lambda edge density graphs. Then I normalize by n choose R, the total number of KRs. Then I take the limit and let n goes to infinity. Doing so, basically, I just cared about lambda, the edge density. I don't really care about M anymore, right? So looking at this parameter, basically, if we know, suppose why we call it asymptotic, because if we know this guy, right, then this guy plus little o1 times n choose r is precisely our function, right? So you can solve the original problem up to a negligible error term. You can solve it asymptotically. I'm just rewriting it, this definition. Here comes now the picture promised. So now I'll just draw this triangle density. So what it means is the number of triangles normalized by n choose 2, n choose 3. Here I draw the edge density, which is the number of edges, m, normalized by n choose 2. So the picture looks, let me first draw the picture. Well, of course, the density does not go above 1. I normalized it. So I have 1 and 1 here. Within this box, okay, so what's going on here? Well, okay, let's explain. The x-axis is the edge density of our host graph G, and the y-axis is the normalized triangle density. So this region here is all the permissible triangle density given the edge density, okay? That's the upper bound here. Upper bound follows quite easily by cross-Kakatono. So what is upper bound? The maximum number of triangles given m vertex and m edges. You basically, by the shadow theorem, you want to pack them as compact as possible. You just make a clique, okay? So that's the upper bound. So the minimization is what we care about here. Mantel's theorem tells us that up until your edge density is 1/2, we do not expect to see any triangles. So this is why there's no growth. Oh, okay. There's nothing going on before 1/2, right? Okay. So it dormants here. It's 0. up until 1/2. Then we start to see triangles. This is the triangle density. And this yellow line that I'm drawing is actually the normalized count for this guy. Okay, let me call it H sub R. So this is the H sub R of lambda if I normalize it. So why this question is difficult? The first difficulty is that the conjectured value, little hr, even for the asymptotic one, for the little g, it consists of countably many pieces of concave shape, right? All these parts is concave going in, and they're countably many. One piece for each interval of interon density. And as a result, there's a countably difficulty number 1. There are countably many singularity. Okay, what do I mean by that? So let's take a look at this particular point. Okay. This is in transition between right around 3-partite graph, Turan graph, right? This is 2/3, yeah, 2/3 is 3-partite Turan density. So what do I mean by the singularity? What is the slope of this yellow line? The slope. The slope is precisely when you add an edge, how many triangles you will see more, right? It's kind of the increment. It's a derivative. It's the increment. So the derivative here is not differentiable. There's a singularity here. Because if I say combinatorially, right before you hit n squared over 3 edges, let's say n3 over 4, n3 over 3 minus 1 edges, you have almost everything, but you still have room to put on a single edge to increase the size. Now you put on this to increase the size. The additional number of triangles you will see is just n over 3, right? But if you go above, you have no room. If you now above, let's say you already have this many edges. Now there's no way to put it in between. You're forced to put it, let's say, inside. Now the number of triangles you create is 2n over 3, right? The slope suddenly changed from n over 3 to 2n over 3. This is what I mean by singularity. And there are countably many of them. Okay. And of course, the difficulty number 2 comes from what I described earlier. Is that there are actually a large so there difficulty number 2 is can be seen through this large continuous family of non-isomorphic minimizer. What I mean is that here you can do whatever you want. You can change to any triangle free graph you want. So you can change it in the whatever continuous means, right? So there are you can make them non-isomorphic. There are many different types in some sense, non-isomorphic minimizers. Okay. Right. Okay. So now we finally get to the history part. So history part 2. Let's focus on this picture. What do we know about this problem? We just basically reintroduce the problem in the asymptotic setting. What do I know about this one? So there are actually lots of people I was about to write down, but I'm not sure if I can finish on time. So let me just read it through. For example, at the beginning, there's Goodman's bound, and Moon and Moser work on it in 62, Nordhaus Stewart in 63, and then the next one I do want to mention is by Bolobach. So Bolobach obtained the first kind of bound, which is piecewise linear. So this is Bolobach bound, lower bound, okay? So he showed that if you look at every two consecutive two-round density, instead of this concave scallop that you put there, if you put a straight line there, then this is a bound. Not quite there. You still have this room to jump, right? So this is Bolobach in 76. This is one result I want to highlight. And then Fisher in 89, he basically resolved the first piece. Okay? This piece is by Fisher. Shows that the first scallop is really the minimizer, the minimum asymptotically. Okay. Then the breakthrough come at Razborov paper in 2008. Basically, he solved all the determining G3, this G function. Okay, the triangle minimization problem. He showed that this yellow curve is indeed the minimum curve, the minimum density, the boundary, the minimum triangle density. And this is where one of the earliest application of the flat algebra machinery that he came up with. Then after that, there's Nikiforov in 2011 determining G3 and G4, so K4 minimization. Finally, Christian Reiher in 2016 resolved all the other cases, all the clique minimization problem. So showing that it is similar to the triangle case. All the extremal example, one of them must look, oh no, sorry, we don't know anything about structure, but just look at the numerical value, the minimum density, it is predicted as those, equal to those graph, okay? We just know the value. So the value, it is true like that. Minimizer. Okay, so the minimizer, right. Exactly like that. You have some parts. All the parts are equal size. And there's another part that's smaller. You complete within. Complete to it. Then you can change two parts to triangle free. Right? Depends on the edge density. Then you can determine the number of parts. So that's what they prove. It equals to that. Now, let me get to the main results that we obtained on this topic. The first, it's about the exact result. So far, this is asymptotic, right? We just know the value. We don't know anything about the structure. We do know what's the amount of triangles or fixed size clique you're supposed to see, but how the graph look like, we don't. The original conjecture we still don't know, right? So the first result is of this type. Basically, so the first one is the exact type of result. This is by me, Oleg Pikhurko, Catherine Staden. A few years back we did this, and this year it was accepted. So we proved that at least for the triangle minimization problem, for the triangle problem, we characterize all minimizers, provided that the edge density is strictly less than 1. Somehow, strangely, counterintuitively, when the graph, the number of edges get very close to complete graph, we cannot do it somehow. But a part that measure 0 interval, all the other parts, whenever you have edges up to n choose 2 minus epsilon n squared, we can characterize exactly how they look like. And this is indeed one of them. Okay, there are several other families, but too technical to write down, so I'm going to skip it. So this is the first result about the exact results. Before this one, the only exact result we know is this tiny interval around each countably many points we have here. Okay, so that's basically measure 0 sets. And the next one I want to talk about is, what about larger clique? So now we know precisely the triangle problem. We know the extremal structure, the minimizer. What about larger ones? So that's the next one. For larger clique, we know the asymptotic structure. Okay, what do I mean? So this is work with Jae-hoon and Marian Sharifs, okay? Or maybe we did it 2 years ago. What we prove is that, not the exact result, but what we're saying is that for all fixed size clique, before I write down, let me just mention, for all R that you pick, if we are given the edge density, if your clique density is very close to this yellow line, is very close to minimizer, your approximate minimizer, then actually you are also very, very close to this type of graph. Okay? You can change little o n square adjacencies to go to this type of graph. Okay?
It's kind of stable.
Stability type, sure. So showing that approximate minimizer are as predicted. Okay, so this basically asymptotically answers the conjecture back, Lovász and Shumno's conjecture up to this little n square adjacency. Okay, and maybe there's a little bit time left. I want to briefly mention. I will not talk about this one, but maybe briefly mention how we go about showing these type of things. Just a few words. Any questions, though, before I...
Does your proof depend also on flag algebra, or is it?
Implicitly, yes, because right. So the approximate the stability that you said, we can also call our result here stability result. It was known for triangles. This is by Oleg, Pikhurko and Razborov. They use flat algebra to get a stability. And our result, use their result as black box. So I think that's yes, right? So our result, actually stability result, uses both this stability for triangle and also Christian's result on the clique density theorem, the asymptotic, as black box. So let me just say a few words very briefly about the ideas. So we can conclude for today. For this result. Okay. Proof ideas. Okay, so the idea is basically the first observation is that we have a triangle minimization problem and clique minimization problem for larger fixed size clique. One first thing to notice is that if you look at this conjecture by Lovász and Szymonovich, it doesn't say anything about the clique size, right? It just say that fix your clique size R, then one of them minimizer look like that. So their set of minimizer is almost the same, right? It's something like this. So they have the same set of minimizers. So what, you will ask? Same size of minimizer. But what do we know? Well, okay, then we can do the following. We can start our graph G. We want to prove approximate structure, right? So now we can start our graph G. That's KR approximate minimizer, right? We want to say something about graphs that has approximately minimum number of KRs. So we start with one such graph. And now, because of this, we can assume the graph G is not triangle minimizer. Because if the graph G is approximate triangle minimizer, then all like Pikhurko and Razborov's result on triangle stability already tell us that they have to look like that. So we can suppose otherwise. This is how we explore the first bullet point. So we can assume they are heavy on triangles. Okay? That's basically how we explore the first one. Because this problem for asymptotic structure, we already solved it. So if you are not heavy on triangles, minimum, we are done. So we can suppose otherwise. Next, okay. And the next is, if you look at this scallop, it's really difficult because there's concatenating discontinuity. But this is the result of Lovász and Simonovich. They solved all these little pieces around Turon density. That means we can just focus on one of these scallop, right? So if we focus on one scallop, this piece here is differentiable with respect to the edge density. Okay, it's very smooth. So what can we do about it? If it's differentiable, then we can use this variational principle to derive some useful property of our minimizer. Okay. So what I'm particularly saying is that you can use, for example, Lagrange multiplier method to derive a relationship between a mesh So what I mean is you can derive certain relation using Lagrange multiplier method between, this is the number of K2 containing a fixed vertex X. So between the degree of a vertex and the number of KR containing a vertex, there's some relation that you have to satisfy for this particular graph that we start with. Okay? And the Lagrange multiplier method basically in the combinatorial way, basically saying that if you don't satisfy this linear relation, you can somehow massage the graph in a way that violates the fact that the G is minimized, approximate minimizer. That's basically what it says. Okay? Then we are almost done, because then what do we know? Now we're going to make use of this relation. We know that we start with a graph that's heavy on triangle. That means I can find the vertex X that's in many triangles, because it's very heavy on triangle. If it's in many triangles, what does it mean? That means here, the edge density is very heavy, right? It's large. Larger than you would suspect. The triangles containing X transfer to the edge density inside its neighborhood. And the KR containing X transfer to KR minus 1 density inside this neighborhood. Then finally, we will derive a contradiction using Clique density theorem to the linear relation that we established in the first place. And that wraps up the proof. Okay? So I will stop here. Thanks for listening.
Okay. Any questions?
So you say you don't characterize the minimizers when the edge density is very close to 1.
Right.
But I suppose when the edge density is sufficiently close to 1, then you could still do it. Like, if it's a complete graph minus 3.
Minus n over 2 or something, I think.
Okay.
Some linear times n. But already a large constant times n, we don't know.
Aha.
Yeah.
Interesting. Is there a conjecture?
Our conjecture is in
Oh,
this
it's
paper.
still this, of course.
Yeah, it's the same one. And I think we even have a lemma saying that if you can solve this particular regime, there's an easy reduction to solve all cases even. So if you can solve very close to 1, it actually implies the whole interval.
Okay.
Yeah.
Give a different.
There's a way to do it. Yeah. At the concluding remark of our paper. So. Yeah.
Going beyond cliques, is there something interesting like color critical graphs or something? This kind of
Oh, right. So I think there's definitely some research done. Not so much. I think Dhruv Mubai has some paper on color critical ones, given some density. He did something on these. But not so much. There are some, but not so much. Yeah.
color critical meaning?
So there exists an edge. Upon removing, you reduce the chromatic number of the graph, I guess, right? So for example, C5 is color critical because you remove any edge from C5, it becomes too colorable.
These are nice because the Theorem number behaves like the corresponding clique. So Theorem number for C5 is exactly like triangle.
Yeah, because this edge is done.
Yeah, I guess that's a natural next thing, but probably it will also be difficult in some sense. But I suspect lots of technique here can be applied, but without working on it, I can't really say much. There are some literature.
But the complete particles, maybe the problem will be really hard.
Complete, yes, that's basically Sidorenko's conjecture, right? You given the edge density, you want to count fixed size per product graph. Right, that's very difficult. And,
There's a question from the chat. Any applications or implications from your results?
Oh, there's even a chat. Okay. Finally, I go YouTube live. So application, implication. I guess on top of my head, no, because when we start working on this problem, we really just try this type of set of problems, and perhaps some of the techniques here can be used for the exact structure for larger cliques. That's we are very positive about, but this is already 140 pages, so we don't feel that positive about trying this technique on the larger clique. This is only for triangle, so for larger clique, you will get more complicated. Yeah. So, but for other type of problem, maybe for some other similar as what Casey that maybe color critical or some others. But I don't directly see a link to very different looking problems. Not quite.
Any other questions? Okay.
I was just thinking, so I guess you go from the question of just fixing the number of vertices and trying to avoid triangles, and then you fix the number of edges as well. But what if you fix the number of copies of smaller cliques and then?
Yeah, that's a very interesting question. Actually, we were talking with Oleg and also Christian visited ones, and we feel like, yeah, it's very natural. For example, it's still open. If suppose we give an n vertex graph and you fix your triangle density, what is the minimum k-fold density? And perhaps it still look like this, but even for this simplest case, we don't know. So I think it's also interesting. Perhaps lots of technique here can also be applied there. This is definitely open and quite natural. Yeah.
Any other questions? Okay, let's let's thank the speaker again.